Welcome to Quick and Dirty. The topic today is light, and as many of my videos, no fancy animations or pictures or anything, so basically you can close your eyes, concentrate and listen. So what is light? Light, from a physical standpoint, is something very special because it contains two properties at the same time. It combines properties of a particle and properties of a wave. And in this tutorial, I will only talk about the wave properties. So, what is a wave? I'm here in Lima, and basically here's the ocean. And some weeks ago, I was swimming in the ocean, and of course, you know that water moves in waves. And while I was swimming in the ocean, I had this surreal experience. When the waves are relatively high, for example, like 2 or 3 meters, and you are, let's say, 200 meters out of the shore, the waves are that big. And basically the water is like moving under your body, okay? So the water lifts you up, and when the wave is gone, you go down again. So the water have hills, or a wave has hills, and a wave has valleys, okay? And when you are on the hill of the wave, you can see the whole ocean. You feel like, I'm the king of the world. And 1 second later, you're in the valley and you don't see anything. You see only water around you because you're on the deepest point of the wave. And you feel a little bit lost because you have no reference point. You just see the water hills around you. And 1 second later, you're on the hill again, king of the world. 1 second later, I feel so lonely. Okay, anyway, so this is how a wave basically moves, okay? A wave moves or has the shape, the pattern of waves and valleys. And each wave has specifications, okay? I just call it specifications. One I already mentioned is the amplitude, which means how high or how big is the difference from the highest point to the lowest point, okay? So I was just talking like the waves here in Lima, they are around about like 2 to 3 meters, okay? From the highest peak to the valley. But today I will totally not talk about the amplitude. I was just mentioning it for complete purposes. Okay, the next specification is the wavelength, okay? So for example, if you would sit on a boat and you would see me swimming on the wave, I couldn't really see the wavelength because I'm in the wave. But if you look from far away from the profile, you could see the distance from one peak, and come to valley, to another peak. So from two same points, from two peaks, or from two valleys, the distance, or where it starts, go down to the next starting point. Okay, this distance, this is called the wavelength. So you also already know, the further out you swim on the ocean, the longer the wavelengths get, okay? So for example, if you have a tsunami, they can have wavelengths of several kilometers from one hill to the next hill. And if you let drop a water drop in a glass of water, these are very tiny waves. Not talking about the amplitude, not talking about the height, only talking about the distance from one peak to the next peak, okay? And there is a third basic property of each wave. This is called the frequency, which means how many of these peaks or how many of these valleys, basically how many of these iterations, which is called oscillation, how many of these oscillations fit into a special space, okay? And you can already imagine that the wavelength is opposed to the frequency. Okay, what does that mean? Imagine you have a spring fever, okay? You take a pen, a ball pen, and you open it, and inside there is this spring, right? And if you watch the spring from the profile, you cannot see the curls, okay? By the way, the curly hairs also have a wavelength, okay? If you see the spring from the profile, you only can see this wave pattern, right? The hills and the valleys. And if you take that spring, this is like so small, okay? And the distance from one hill to another hill is maybe only a millimeter, okay? Because the spring is very tight together. But if you take the spring and stretch it, you stretch it to both sides, the distance from one peak to another, it gets longer and longer, which means the wavelength gets longer and longer when you stretch that spring. But at the same time, if you take like 1 centimeter of this spring, the longer the wavelength gets, the less amount of peaks fit into 1 centimeter. If you stretch it super long, maybe only one single peak and valley is in 1 centimeter, okay? So the longer the wave, the lower the frequency. So wavelength is measured in a distance like meters, right? And the frequency, the number of oscillations, it's basically for the most of waves, it's measured in a time, okay? How many oscillations can be done in a second? And the number of oscillations in a second, that you don't have to say this all the time, you just say Hertz, okay? Hertz was a physician with the name Hertz, and yeah, basically after him, the unit oscillations per second got the name from this guy, Hertz, okay? Good. So you might ask now, yeah, okay, a water wave, but like light is not water. Right. Light is not a water wave. Light is not a sound wave, a sonic, an audio wave. Light is an electromagnetic wave. Okay, what has light to do with electro or with magnetism? Basically, not much, if I'm honest. All electromagnetic waves, and there are plenty of, I come to that in a second. All electromagnetic waves have one property in common, and this is that they interact all in their specific kind of way with the matter around them. Okay, and all these electromagnetic waves, they basically differ in these two specific things, frequency and wavelength, okay? So what has light in common with all the other electromagnetic waves? Basically, they differentiate only by the frequency and the wavelength, okay? The frequency can go like from 0 or 0.00 something and unlimited, okay? Just the more oscillations per second, the higher the frequency. Good. Okay, so imagine that this spring out of your ballpoint writing thing, This is an electromagnetic wave, okay? And you can stretch it as long as you want, that the wavelength gets longer and longer and the frequency gets lower and lower, or this material of that spring is so thin, okay, that you can press it really tight together, that you have lots of oscillations on a very short space, okay? And this stretching, these differences from very, very super short wavelengths and super high frequency to very long wavelengths and very low frequency, this whole thing is called a spectrum, okay? If you take the spring and stretch it as long as you can and put it as tight together as you can, this is called spectrum, okay? If you do the latter one, which means you press the spring, the electromagnetic wave, as tight together as you can, you get gamma rays, okay? Gamma rays is that what is emitted by a nuclear explosion, okay? And if you stretch it a little longer, that means the distance between the peaks gets a little bit longer, you get X-ray, okay? When you broke a bone or something, you must go to X-ray. Then, yeah, they use this. By the way, I'm using the word ray. So ray is basically like one wave. And if you have like millions of light rays, which go all in different directions and they all cross each other and so on, you have a radiation, okay? Basically, many rays are radiations. And in the example of light, you have like a diffuse light if all the rays come from totally different directions. Good. So we had an example on the spectrum of very, very, very short wavelengths. And if you go on the other side of the spectrum, where you stretch it relatively long, you have, for example, radio waves, okay? Radio waves have, in comparison to all the other electromagnetic waves, very long wavelengths and very low frequencies. So basically, nowadays, we live in a world which is polluted by radiation, because everything that surrounds us, like Wi-Fi signals, Bluetooth, mobile transmission, these are all electromagnetic waves, and this is all radiations, okay? And some of the radiation is more harmful. Can you remember when I told you all electromagnetic waves interact with matter, okay? So you know, gamma rays from a nuclear explosion, they are totally not good for our DNA. They interact very strong with matter. They can destroy our DNA. And some radiation is supposed to be less harmful, like the radio waves. We have radio for, I don't know, 100 years, and I hope that nobody got cancer because of radio, okay? But this is a topic where science, well, actually, I think science is not so far in this topic. Anyway, the question is now, can you see these electromagnetic waves? Or can you smell them? Do you have any sense to recognize them? And of course, you cannot smell radio, right? Or you cannot smell gamma waves. But there is one exception. If you take this electromagnetic spring, right, and you stretch it to a very specific wavelength, suddenly you can start to see electromagnetic waves. And this is called light. On a very, very tiny part of the whole spectrum, there is one wavelength region where we where we can see electromagnetic waves. Okay, so imagine you have your electromagnetic wave, the spring out of your pen, and you have a very short wavelength of, let's say, 100 nanometer, okay? Very tight together, these peaks. And then you grab it and then you stretch it, okay? You stretch it to 200 nanometer. You cannot still see anything. And you stretch it to 300 nanometer. And you still cannot see anything, but you are already in the spectrum of light. And this is called ultraviolet light, okay? This is basically, these are the light rays which makes the sunburn. Remember when I said radiation interacts with matter? So the human eye cannot see the ultraviolet light, okay? But if you stretch it still a little bit longer, like 400 nanometers, it becomes violet light. And this you can see, okay? And then you stretch it longer and you get blue light, you get green light, you get yellow light, you get orange light, you get red light. And when you have it stretched to 700 nanometers, basically you leave the spectrum of electromagnetic waves where you see it, because then the infrared light starts, okay? And you cannot really see the infrared lights. The special cameras, they can see it. You may already know this is called heat waves, okay? So it's not really light anymore. Of course it's light, but this is just a naming, how you name it. For example, remote controls, they work with infrared light. And if infrared light, if this is a heat wave, why isn't a remote control getting warm? Well, this is a matter of energy, okay? How high is the energy level of the wave? Can you remember this amplitude thing? How high is the wave? Well, basically, the infrared light in a remote control has very low energy, so the heat which emits this LED from the remote, basically you cannot sense, okay? But theoretically, yes, these are heat waves. Good. So basically we have two senses, our eye and like our touch sense, to recognize two kinds of electromagnetic waves, which are light and which is heat, but only in this very, very tiny spectrum, okay? All the other electromagnetic waves we cannot sense at all with any of our senses. So how many light colors are there? Well, basically there are like millions, but the human eye, of course, cannot differentiate like all these tiny differences between the colors, okay? So to make it easy, I was talking about these 7 rainbow colors, okay? And all the light which we see from the sun, this contains all these colors together, okay? For example, if you have 6 friends, okay, you all stay in a circle, and each of your friends and you, which are 7 person, each of you has a torch with a very specific color. Like the one has a red torch with only a red light, and the other person only has a green torch, and so on. And you put a white sheet of paper in the middle of your circle on the floor. And the first person takes the red torch and makes a beam on the white paper. And you see, of course, it's dark around. It's dark. And first you see a red spot on the white paper. And then the next person with a yellow torch, she makes the person makes another beam on the same spot, and then these two colors get mixed. So the red spot on the white paper and the yellow torch, they make like an orange spot, okay? And if all these 7 people with all the rainbow colors, they make their torches and make the beam on the same spot of the paper is white. The paper looks white on that spot. Why? Because all these colors together at the same time in the same amount, they create white light, what we perceive as white light. And if you do the opposite, which means you throw white light through a prism is this triangle made out of optical glass, okay? Optical glass is basically nothing than super clean glass without bubbles and so on. You get, on the other side, you get all the rainbow colors out. Maybe you know the cover from the Pink Floyd album. There you see this prism, okay? White light on the one side, and it gets like it breaks into all the rainbow colors on the other side. So if you see the white light of the sun, you might think, okay, so there are basically all the rainbow colors all together in a similar amount, okay? But you also know that the color of the sunlight in the middle of the day, it looks different, okay? It's much brighter, it appears much whiter, and when the sun gets down at the time of the sunset, when the sun is very low over the horizon, the sunlight suddenly looks much warmer, okay? Much more reddish, okay? And this is basically because of several physical, optical circumstances, okay? For example, all the dust which is in the air changes the color and so on. But one of the main reasons is that the sunlight must go through our atmosphere, okay? And when the sun is lower over the horizon, the different colors, the different light rays with the different colors, they get deflected in a different way through the atmosphere, which basically leads to the fact that in the end more amount of the light of the red rays come to your eyes, and the other colors gets a little bit more deflected by the atmosphere, because different wavelengths of the colors, they react differently. Light in different wavelengths and different frequencies get distracted in another angle and in another fashion by the atmosphere. And I already used the word that at the sunset the light seems warmer, okay? This is just wording by human, and this is basically the reason that light colors get temperatures. For example, the mid-sun has a temperature of 5,500 Kelvin, and later in the day at the sunset time, for example, sun has a temperature of 5,000 Kelvin, okay? So far so good. So human need light to see. Of course, also animals need light to see, but human need much more light, okay? For example, cats, they can see much better in the dark, or owls, or basically many of the nocturnal creatures, they have much more sensitive eyes than we have. And what kind of light can we see? Well, basically we can see light from a direct light source like the sun, right? This is like direct light which directly falls into our eyes. But if I look somewhere else, like not in the sun, if I look, for example, at this tree, I see a green tree, right? I see green leaves, but these leaves, they don't shine on their own, right? So why do I see the leaves if this is not a light source? Well, basically this is indirect light, which means the direct light falls on an object and the object reflects the light, and we basically see the reflection of the light from the object. Okay, and why is this leaf green? Okay, why are these leaves green? Basically the question should be, why does they look green? Okay, so what happens there? Well, the sunlight with all of the colors is shining on the leaf, and the leaf basically captures all the colors and reflects only the green light. This is why we see only the green reflection from the leaf. And why is, for example, the bark of a tree, why is that like brown? Why is it brown? Well, there isn't really such thing like brown light. It's basically the bark of a tree. It captures all the colors of the light, and it reflects a little bit of green light and a little bit of red light and a little bit of yellow light, and all this together in a mixture is creating our sense of a brown tree. Okay, so this is called the hue. The hue in photography is basically the color. Yeah, it's basically the color of objects is called the hue. Okay, H-U-E. If you look at these trees, we can also see like brighter trees and darker trees. So what is darkness? Why is this tree darker than this tree? Also easy, because the bright tree, or like brighter green leaves, like this is a brighter green leaf, reflects more light, okay? And the darker parts of a tree or a bark, they just keep in general more of the light, they keep it and they reflect fewer light, which in our perception seems darker, okay? This is, in photography, this is the lightness of objects. And the third thing is, if we have like juicy grass like this, okay? Juicy grass, it's really green. And we have leaves which are also green, but they look more gray. You see, they look more grayish. This is much more green, and this is more gray, okay? This is called the saturation of a color. Basically is you have like a 100% green and you have a 100% gray. And this gray is from the same lightness, okay? That you don't change the brightness of the color. And then you mix this together. The green you mix together with the gray. And the more gray you mix into the green gets more desaturated, or it gets less saturated the more gray you mix in. Which means you don't change the color. It is still green, but it's just less saturated. And you don't change the lightness, the brightness of the color. It's still same bright, it's just less saturated. Okay? If you mix gray in it. Okay, but these were basically only additional informations. In the next tutorials, I will especially talk only about the brightness, okay? How bright or how light do we perceive things? And basically it's the amount of light which falls into our eyes. And of course you may ask now, okay, how does our eye work when light falls into it? This I will cover in the next one. Thanks for watching this time.